The headline screams infinite energy, but the reality sits inside a server farm running complex code, not in a power plant generating kilowatts of electricity. This video dissects why AI models can predict plasma behavior without actually creating it, and explains the massive engineering gap between simulating heat and converting that heat into usable grid power, a hurdle no amount of software has yet solved. When you see a headline claiming Google found infinite energy, your brain immediately jumps to one conclusion: we have cracked fusion or discovered a new physics law that breaks thermodynamics. But before we get ahead of ourselves, let's look at what actually happened. The breakthrough was not in the physical world of magnets and plasma. It was inside a digital twin running on Google's infrastructure. This is a simulation using machine learning to predict how complex fluids behave under extreme conditions, specifically mimicking the chaotic dance of particles inside a fusion reactor core. This distinction matters because calling this infinite energy is a category error. It confuses data processing with physical work. Think about it like simulating a car crash in a video game versus actually crashing a real vehicle on a test track. The simulation can predict exactly how the metal will crumple, where the stress points are, and what happens to the passengers down to the millimeter. But that digital model does not generate electricity from the impact, nor does it create kinetic force outside of your computer processor. One predicts outcomes, neither generates power for a city grid. The confusion arises because we treat software as if it possesses physical agency when it is merely a tool used by engineers. The headline implies that once you solve the math problem in code, nature follows suit automatically. But mathematics describes reality, it does not create it. We can simulate an object accelerating to light speed with perfect fidelity on a screen, but we cannot build a machine that actually reaches those speeds or extracts energy from them because of hard physical constraints. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. According to fundamental laws of relativity and thermodynamics, while mass and energy are interchangeable according to the equation E equals mc squared, converting that energy efficiently remains an immense hardware challenge. As objects approach light speed or attempt infinite acceleration, their observed relativistic mass becomes infinitely large. This requires infinite energy input to achieve further motion. It is a physical impossibility for current engineering because you cannot build a power source strong enough to push something with infinite inertia into the next moment of time. The simulation can show us that limit without breaking, reality hits it and stops dead in its tracks. This brings us to the actual engineering hurdle, which is far less glamorous than infinite energy, but significantly more critical for our future infrastructure. The primary bottleneck is not simulating heat or understanding plasma dynamics on a computer screen. It is converting that thermal energy into usable electricity efficiently enough to be net positive. This requires advanced materials and mechanical systems capable of withstanding extreme temperatures without melting, degrading, or failing catastrophically. Imagine trying to capture the heat from a fusion reaction using current turbine technology. The core temperature reaches millions of degrees. Any material we have today will melt long before it can transfer that energy into rotational motion for an electrical generator. Software cannot bypass this constraint because no amount of code changes the melting point of steel or copper. We need breakthroughs in material science to create containment vessels and heat exchangers that survive these conditions, alongside new cooling systems capable of managing the thermal load without consuming more power than they produce. The scale of this challenge is quantified by the massive capital required just to begin solving it globally. Estimates suggest we will need approximately $2.5 trillion in clean energy investment over 6 years simply to meet global load growth with current technologies. This highlights that solving the problem requires heavy industrial engineering, not just algorithmic tweaks. We're talking about building physical infrastructure, new turbines, upgraded transmission grids, and advanced cooling facilities. It is a story of concrete, steel, and silicon fabs where wafers must be manufactured to withstand these conditions before we can ever hope to scale up generation capacity. Google's actual energy strategy reflects this reality rather than the sensationalized headline. Their recent focus involves matching 100% of their annual data center usage with new, clean energy sources like solar and wind, not generating infinite power internally from a simulation. They are pursuing what they call 24/7 carbon-free energy. which requires physical infrastructure investments and grid modernization to ensure that when the sun isn't shining or the wind isn't blowing, there is still capacity available. This path relies on expanding renewable generation assets and improving storage hardware, not discovering a loophole in physics through better software optimization. The confusion between simulation and generation leads many viewers to expect clean energy solutions within months rather than decades of heavy industrial engineering. If we believe that predicting plasma behavior equals generating power, we set ourselves up for disappointment when the grid doesn't suddenly light up with fusion electricity tomorrow. Understanding that AI is a tool engineers use to design better reactors means recognizing where the real innovation lies in materials science, cooling systems, and power conversion hardware. The code helps us understand how to build the machine. It does not replace the need to build the machine itself. The future of clean power will be built on these physical layers rather than just lines of code. We are moving from a phase where we hope for magic bullets and software to a phase where we must grind through decades of manufacturing, supply chain logistics, and materials testing. The path forward is paved with real-world constraints that demand respect for the laws of physics. Until we solve the heat-to-electricity problem at scale, simulations will remain powerful design aids but not sources of power themselves. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.